So thanks, Haider, for agreeing to write this talk on your transatlantic flights. So for those who don't know him, Haider Abidi is a new staff physicist at Brookhaven who thinks a lot about a lot of different things about how to get our inner detector tracking upgrade working and getting it to actually reach a state where it can be built. But also thinking about how we can use machine learning in new and inventive ways to do tracking, particularly for the trigger system, which is where he and I collaborate. So I asked him to put together some fun slides to think about this sort of the second topic, and I'll let him sort of take it away and wow you with all the cool things he's thinking about. Go ahead, Hyder, whenever you're ready.
Okay. So I know Jared sort of gave me that charge, but I tried to sort of keep it very high level and not go into the super nitty-gritty details of the different things. So I'm going to try to sort of introduce charge particle tracking because I didn't know how much background everyone had. So there will be a bit of that. And then there will be a bit of why machine learning and why we should think about that in different contexts. So that's sort of what this presentation will be about. And again, if you guys have questions at any point, feel free to poke me in the middle and we can sort of try answering them. So, okay, this works. So I think the fact that you guys are here, I don't have to convince you the fact that machine learning has transformed basically every field that we know, like in and out of physics, right? And it sort of changed how we think about it, how we approach problems, and how we interact with the world. But in all of these things, sort of the questions that I've sort of tried to focus on and figure out is like, why has this done it? Like, what's so important about machine learning that has created this transformation? And in some sense, sort of the 3 points that I have listed are sort of my very biased thesis of why this has been the case. So the reason why I think machine learning has transformed all of these fields is because it's a very easy way to encode sort of a complex algorithm. So something that might have taken days or years to do before can now be done very fast or very quickly. There's also new technology that is being designed for machine learning that makes it very fast to sort of actually evaluate and run these algorithms. And then also, machine learning is sort of a completely different language in how we think about problems. So it allows us to sort of rewrite problem statements and think about problems in a completely different way. But having said that, I want to say machine learning is not a magic solution in any sense of the way. It requires a ton of effort from a lot of people to make it work. It's sort of because it's a new language and a new field, there's always tiny little issues that pop up. And then, you know, in sort of physics or in any other things, a lot of things have gone on for a very long time. So there is a lot of sort of what I call structural barrier in sort of putting ML into these big, ginormous frameworks, whether it's software, whether it's hardware, it takes a lot of time. So in some sense, this talk, like I said, will be sort of a version of the why and the but in the context of physics and how machine learning has changed how we approach problems. And like I said, it's very light on the exact details, which I'm happy to fill in, and the focus is more on global details. So I have one slide on the power of ML because I'm assuming if people are here, they know ML and what it's done. So I always find it really crazy that now we're at a stage where we can give ML a tiny little prompt and it creates a ton of pictures. So there's a lot of possibilities that we can do with machine learning here. So that's the only advertisement slide of ML. So now going back to particle physics. So I wanted to introduce particle physics again because I didn't know what the background for everyone is. So I'm just going to start from the basic question. So the thing that we want to try to study in particle physics is the two sort of questions or three questions that are like, what are we made of? Why is there matter in the universe? And how do we continue to exist? And in some sense, there's a mapping of all of these questions to what we can actually study. So on this slide, I've shown you what is the standard model of elementary particle physics, which is basically the periodic table of all the fundamental particles we know. So if I take those questions that I have on the top and then map it onto this picture, it basically leads to the question of what are these fundamental building blocks and how they interact with each other. So everything we do in particle physics is trying to study these I don't even know, can't count, particles and how they all couple with each other. So the question is, how do we study this? And there is a very, very simple way we do it. Our simple idea is that we take two protons together and smash them and see what comes out of it. And the reason why this works is because of sort of special relativity and then quantum mechanics. When you smash these two particles together, there's a lot of energy that is condensed in this very tiny spot. And then what comes out at the end is a whole bunch of other particles that we can study and interact and measure, and then try to answer the question of how the particles interact with each other. And the way we do it is there are very big accelerators that collide these particles at very high energies, and then there are detectors that measure the particles coming out of it. So you guys can't see my mouse, right? No.
No, I was looking to see.
Okay.
Yeah.
Yeah, okay. I don't see it either. But the picture on the left is what the particles come out, and when we do a detector around it and build a detector around it, and then we sort of measure the particles, and then we have a lot of analysis techniques to understand that picture and derive scientific results and convert the picture on the left to the picture on the right. And the picture on the right is, again, mapping onto the standard model of particle physics. So this talk, like I said, is the machine learning at the intersection of the two. So what do detectors measure? And then what are the analysis techniques that are needed to convert this picture from the left to the right? And this is where I'm going to be sort of focusing the machine learning part of this entire talk on. So then filling in a bit more detail. So the thing that I work on with Jared is the Large Hadron Collider. So the big ring that you see is this 27-kilometer proton-proton accelerator. And just as a reference, I've tried highlighting where the Geneva airport is on the bottom left corner there. And in this sort of collider, we have two proton beams that are at 6.8 TeV. And to give you some scale, 1 TeV is roughly the equivalent energy of sort of a flying mosquito, which doesn't seem like a lot, but once you like squeeze it down to a very, very tiny area, it actually creates a lot of particles that come out of it, and we can study a lot of things in this accelerator. And then if you notice, this ring crosses at 4 different points, and each one of those points, you see the two sort of rings intersect, and that's where we have particles that collide with each other. And around each one of these collisions, like I said, we have some detectors, and in 2 of them we have ATLAS and CMS, which are general purpose experiments, and then ALICE and LHCb are 2 sort of specialized experiments. But I work on ATLAS, so we're going to be talking about ATLAS a bit more. So ATLAS, like I said, is this general purpose detector at one of the LHC's interaction point. And just to sort of give a scale, if you notice on the picture at the sort of middle part, there are these 2 people, just to give for reference for scale. So it's a very, very ginormous detector that's built around these collision points. But the thing to sort of note here, if you can see the different colors, is that each color represents a different detector. So it's not one ginormous piece of machinery. It's actually a lot of different technologies that are inside that are each designed to provide sort of some complementary information of the particles that have traveled through. And only once you put together all of this information do you get something, do you get enough information to understand what actually happened at the collision point. So just to show you sort of a slice, this is a sort of a transversal slice of the ATLAS detector, and you can see different particles like muons or photons or protons or neutrinos or electrons interacting differently within the different detectors. And like I said, when you combine all of these together, you can actually figure out if a particle that went through your detector is a proton or a muon or an electron, and then you can use all that information back into your analysis and then try to understand what actually happened in the collision. So our focus actually will be on the most innermost detector. Like, so if you see on the picture, there's a tiny part labeled tracking at the bottom left, and the work that Jared was talking about, the work that that I do is sort of trying to do machine learning in using the information that is detected from the tracking subdetector there. So just to give another tiny bit of context, so how do those detectors work? So those detectors are actually made out of silicon sensors. So when a charged particle goes through one of these silicon sensors, so in this picture it's represented by the arrow, it actually ionizes the material. So it creates these positive and negative charge pairs. And then if you sort of put enough bias into the voltage bias into the system, you can actually collect this ionization as a current signal. And once you observe a current signal, it actually means that a charged particle went through that sensor. So this entire tracking detector is lined up with these sensors, and whenever a particle goes through, we see a signal and we know something went there. Yeah, so on the left, you actually see the layout of the silicon sensor. So each one of those panels that you can see is a silicon sensor, and we sort of line them around the interaction point. And then as you can see on the picture on the right, when a particle goes through sort of a different layer of these, it leaves a signal on each one of those layers. And if you can sort of correlate or put together those three into a pattern, you can actually reconstruct the trajectory of a charged particle throughout the entire detector and all of it. So that's sort of the fundamental principle of what we're trying to do. We instrument our entire area around the collision points with some silicon detectors, where if we see a signal, we know a charged particle went through. And then we try to sort of do pattern recognition on all of those signals that we've collected to reconstruct back the trajectory of the charged particle that went through, which again connects back to the physics question that we're asking. So at this point, you might be asking, why is this a hard problem? Well, it turns out when we actually collide things together, it's not just one particle that comes out, it's a ton of them. So in this sort of slice picture of sort of a simulated event, you can see each one of the green tracks is a charged particle that went through. And then each one of these hits, or the yellow sort of symbols that you see, are a detected signal in all of them. So if you sort of just want to count roughly, you see that there are 500,000 hits kind of like this. So if you can think about doing the pattern matching with 500,000 of these signals, you can see this is a combinatorial problem where the computational complexity grows very, very quickly in all of this. So it's a very difficult problem just because of the combinatorial and how dense the event is in all of this. So just to give you sort of one tiny slide on the tracking and how we currently do it. So what we currently do to actually convert the hits back into the track is something called the Kalman filter. And this is sort of a algorithm that was taken or was developed for tracking planes in World War II. And that is something that we still use nowadays. And the way this works is when we have sort of a detector, we can make an initial guess with some sort of precision on what that guess is, where a charged particle went through. And this sort of, you extrapolate to the next sort of surface, then you see a measurement, you update your parameter and the error, and then you sort of just repeat that process, and you can sort of see that represented in each one of them in this picture here. And then once you have all of the measurements that have been detected through the experiment, you see at the end of the sort of the entire chain, you have a very precise determination of the track parameter, the error, and you get the information that you want from this detector. So this is an algorithm which, like I said, World War II, so it's been over 50 plus years of research into this algorithm. It's been tested in high energy physics and satellite experiments and radars and whatnot. And a lot of work has gone into it. So it's extremely precise, it's extremely optimized, and does the job really well. So for all intent and purpose, we have something that works within the Atlas detector that can solve the problem of making tracks or detecting tracks or getting the information from the hits that we measure. So at this point, you might wonder, if it isn't broken, why do we need ML? And this is sort of the rest of it is trying to motivate and answer that question again in more details. So one of the things is that the LHC, the collider that we have, is very close to or exceeding its design parameter, and then the luminosity doubling time, which is the data that we have collected, is increasing. So, and then the accelerator is getting damaged. So there's a lot of reasons of why we would want to upgrade this one. So there's a plan for an upgraded version, which is called the High Lumi LHC. And the idea is that, again, we replace our detectors, we replace the aging components that are there, but at the same time, we also increase the rate of data. So you can see the picture on the bottom left is what it looks like currently in the Atlas detector. So those are the sort of the density of tracks. The expected environment is what's on the right. So you can see the density of the tracks that go through the detector goes, I don't know, a couple factors, maybe an order of magnitude. So like I said before, it was a combinatorial problem. And if we increase the density, it's just gonna make the problem even harder to solve. And just to show you in actual sort of measurable quantities how difficult this problem becomes. So on the x-axis is the sort of the year of running of the Atlas detector, and on the y-axis is sort of the computational time the tracking will take to solve the sort of the problem that we have. And you see in about where the 2026 point is, you see there's a ginormous rise in the blue points, and the that show you, sorry, 2026 is when the upgrade will happen, and you see right after that the amount of computational time increases more than exponentially, which is shown by the black line. So the computing requirements for this tracking at this upgraded environment will blow up. It's not something that is sustainable within sort of the scope of things. So the question then becomes, now that we have ML that's around and, you know, been used everywhere else, can we use ideas from here to tackle this problem? So in sort of trying to answer why ML for tracking, the answers that I have sort of fit into these three boxes, which again, if you connect back to the introduction, sort of can fit into this one. Why do we want to use ML? So in some cases, like in the first box of it, you want to use ML because it can lower the developmental time of writing complex algorithms which can solve these issues at the high Lumi. So can we push performance there? At the same time, the middle box is talking about new technology. So there's a lot of discussion that's going on, like, for example, Google or Amazon or Microsoft creating new silicon hardware, which machine learning is very suited for. The hardware is designed to execute that. So can we leverage the ML language to use these new technologies in our detector? And then the last box, like I said, is rethinking assumptions. Can we rethink the ideas that are in the common filter, which have worked very well until now, but don't scale well? Can we rethink those and try to sort of reorganize the problem where maybe it doesn't blow up that badly? So I'm going to try to show you examples of each one of these boxes. And I'm giving you sort of three specific ML projects that will fit in each one of these boxes. All of the examples will cut across each one of those ones, but I've sort of tried to take liberties to fit in each one of these specific ones, and then just try to highlight that one specific part to show you how it fits within that example. So first one, pushing performance. So like I said, one of the very first parts of the common filter is that you need an initial guess to actually propagate and update that as it sees new information. But it turns out this initial guess, or what we call seeds, requires a lot of human fine-tuning. And the reason why it needs this fine-tuning is, if you look at the picture on the bottom left, I've sort of made a cartoon version of the detector and some hits in it, which are represented by the red dots. And the seeds are basically trying to make triplet combinations of those ones. And I've tried labeling the true ones in yellow and the fake ones in sort of these red boxes. And you can see, like, if a collision happened in the middle, you kind of expect all of these seeds to be pointing towards the center, but the red ones don't. And to make this sort of selection, someone, a graduate student or a postdoc or an undergraduate student, have to sit down and tune the selection. It has to apply cut on this angle or that angle. And then for every one of those variation that they do, they have to run simulation, they have to see all the efficiencies, and it just takes a lot of time to tune this one. So the question in MLSP becomes, can we use ML to predict the direction of the particle and remove the years of the development time for the fine tuning? So here I show an example on the left, which is published in sort of the paper that I've linked here, is that, I mentioned to you about charged particles going through a silicon sensor and then the current being detected. Well, it actually turns out the current that is detected from the sensors actually depends on the direction of the particle. So in this sort of graphic image that you see, you can see from the side view, if the blue particles goes in a direction sort of at that angle, the most amount of current is in the middle strip, and then the two other ones have lower charges there. So we can use ML, feed in this information, and actually detect or predict the direction of this particle. And this is information that we can use to remove bad guesses from the original set. So again, the idea of this machine learning one is that you can generate data, you can put it into an algorithm, and it removes the need for someone to sit down and fine tune, because they can use the data to predict what the actual true particle is already. And just to show, this is an example of how much improvement it could be. So in this plot, you see efficiency and purity. So basically what you want is purity to be as high as possible. So it means that you don't have a lot of bad guesses. And then efficiency is how accurate those guesses are. And you kind of want that as high as possible. So the red point that you see here is someone sat down by hand and tuned it for this data set, and you can see it sort of lies there. But the green curve is a neural network base. So someone with a couple people were able to have an algorithm that can have a potential factor of 5 reduction. They didn't need the 50 years of research in the common filter. They sat down, did this, and were able to do something that could make things better by a factor of 5. So that's sort of one example of pushing performance. The other one is new technology. So like I said, there has been an explosion of very dedicated silicon hardware to evaluate ML algorithms. And I show sort of a picture of this device from Xilinx, but the actual sort of what it does is on the right. So if you look at that graph, you'll see that on the x-axis, there's different silicon technologies, and on the y-axis, it's how long it takes to process an image for some neural network. And if you see the CPUs are on the left, and they can only process sort of about an order of 100 images per second. But if you look at some of these new technologies that are coming from Xilinx, you can see it's a couple orders of magnitude larger, can process 4,000 images per second for this for this setup. So in some sense, ML is very suited. People are designing a lot of technology. So the question here becomes, can we as physicists design ML algorithms that can leverage these technologies in our detector? But again, this stuff doesn't come for free, because this is something that we have to develop a lot of information for. We have to have complex workflow management. We have to install it in the Atlas detector around it. So it takes a lot of work to make something like this happen. But if we can make this happen, we can potentially see a very large improvement in the computational performance of the system. So one example is, let's say I talked about the common filter. What if we want to replace it with something that is ML based? So let's talk about why the common filter works. It's the standard go-to because, like I said, tons of research has been done, and it's a very precise algorithm, but it requires a lot of information about the environment of your detector. So it requires to know where the detector is located physically in real life, and it also needs to know what the magnetic field is around. And these are the two information that it needs, and these are very, very slow and very, very memory intensive. So the question becomes, can we train an NN or a neural network that can encode this information and predict this sort of propagation that we talked about before? So sort of in this picture, I want to show sort of an example where let's suppose you have that initial guess, which we have cleaned out using the information that we have before. Can it predict, for example, where the track would go? So in this case, it's represented by the green dot, and then you can search around this sort of air or this predictions and try to make track candidates that you are trying to do for this tracking. And you can see sort of an example on that right there. And again, the reason why we want to do this is because we can reduce sort of the expensive computation that's inside the common filter to a matrix multiplication that can be performed very efficiently on FPGAs and GPUs. And just to sort of pry this apart a bit, the reason why these devices work is because CPUs are not inherently parallel compute devices. So if you look at the graphic on the bottom left, you see when you're trying to execute an algorithm, it's sort of very linear. You have to do one instruction, then the second, then the third, and the second one only starts when the first one ends. So if you're trying to do something multiple times, the total sort of time it takes to execute an algorithm n times, it's n times the times that it takes to run it once. However, on these sort of FPGAs or these new algorithms, they're designed to be inherently parallel. So if you look at the graphic on the bottom right, you can see it can execute different parts of the instructions concurrently. So while it's processing instruction 1, it can start doing instruction 2 if it sort of finished the first part of that. This sort of reduces that multiplication to an addition. So the total latency becomes the number of times you execute it plus the time to use it once. And this gives you a significantly better computational scaling if n is sufficiently large. And like I said, we're moving into a regime where the behavior is blowing up, and we're sort of hitting that regime where it might actually be faster to encode this information into an ML and then put it into this type of inherently parallel structure. Then you can think about the last bucket, like I said, is to think about the assumptions that goes into these things, into these big systems, and ML can allow us to rethink about this problems. And the reason why that can happen is, like I said, ML is a different language, so we can try formulating in this new language, and then see if we can tackle this problem slightly differently. So in terms of tracking, it's an inherently geometrical problem. And one of the advantages of ML is that there are geometrical ways to encode this. So there's an example that I show on the bottom where you can take the hits information that we have, make it into a computational graph, and then use neural networks, which are very efficient at traversing these graphs, and evaluate them quite efficiently. And the idea with this is you embrace sort of the combinatorial blow up, but you represent them in a very efficient memory way. And then you use the computational power of the neural networks that I showed before to traverse this very fast. So it's trying to take the global problem of the tracking and try to make limited local problem decisions where you're just talking about one hit and its neighboring hits. And this is sort of an active area of research, so I'm not going very deep into this one. And there are people that are trying to make this entire chain working. And the idea here again is, can we use the new ML to reduce the overall complexity and maybe reduce the combinatorial blow-up that we see at the high linear latency? So that's sort of the general idea, and I wanted to recap before I end and open up for questions. So just to say, how did we end up here in this sort of ML world where the questions I was asking? So the idea began with, we wanted to study the fundamental building blocks of the universe, which meant studying those particles and the interaction with them. And the way we wanted to do them is we wanted to smash protons together and put energy in a very tiny area and see what comes out of it. And to do that, we had to put some detectors and measure them, and then try to convert the electrical signals that we measure to the actual physics that we're trying to study. Now, to do this, we actually have a system, but we want to do better, which means we're going through different upgrades, which will make the problem significantly harder, make the computational profile, like I showed in the middle, rise faster than exponential, rise faster than what our budgets can sustain. So the idea then becomes, can we use ML, which is being developed across everywhere, to test new ideas and try to improve the situation? Um, and like I said, when I think about those things, the answer to that falls in these three buckets that I've tried putting it here. So pushing performance, incorporating new technology, and rethinking assumptions. It's not just about the flashy new idea of ML trying to solve a crazy problem or a very different problem that no one has ever been able to put into sort of a computational algorithm. Here it becomes, can we use the power of ML to improve our current ideas? Can we save developmental time and allow people to be more creative, not use a ton of graduate student or undergraduate student time to tune slightly small things? The other question is, can we transfer information from different domains into R? So like I said, Google, Amazon, Facebook, all of these big companies are doing a lot of studies and research into ML. Can we use that information into ours? And this technology idea sort of feeds into one of them. And then the computational needs, the one thing that I didn't mention, the other thing that can happen is we don't have to reduce computational need because it's sort of blowing up. We can also just reduce it to reduce sort of the carbon footprint of our big experiments that we're running. And the last one is, like I said, the example of Common Filter. It's sort of an interesting one where there's 50 years worth of research that's been done. That makes it very efficient and very powerful. But can we use this new ML language to challenge some of those assumptions that are baked into a complex system by people before us? Maybe we can come up with a different solution that takes us in a completely different way. So hopefully I've tried sort of answering why ML and tracking and how I like to think about problems in a different way than the traditional way that people have been trying to use ML in the world around us. So just to conclude, I think tracking is a very complex and interesting problem. It has taken decades of work to optimize it for our current setup. But like I said, machine learning is offering sort of a new way to think about this one. It allows us to incorporate information faster, allows us to sort of leverage improvements from different domains, and then maybe create sort of a different way of breaking the problem down. So ultimately, I think the goal of all of this is to create sort of new ways to improve both the physics and the computational performance. And there's countless different ideas. I've tried to just highlight a couple of them, but it'll take a ton of effort and research to incorporate them into the current and the future experiments. Yeah, and that's sort of all that I prepared for this. Happy to take questions and provide more details.
Thanks, Haider. That's great to think about. Thanks a lot. So I had one or two questions, but I'll leave it. Hopefully some of the students want to ask a question or two. No, come on, students. I can jumpstart it by asking one or two. So I guess one, which is I guess related things, is is there anyone outside of like Google that's actually using tensor processing units? And do you know of anyone who's like an actually, scientific research that's actually using them? Or is it something that's just thrown on slides and we say one day we could use them?
I learned right before coming to this presentation where I was talking to a friend, they're actually trying to put in IceCube, which is a physics experiment down south, right?
Okay.
And they're trying to do real-time learning to detect shower shape evolution, basically doing a fit using the TPE units, because a fit is a matrix multiplication in the end.
That's interesting. My understanding was that TPUs were something that Google built. So I guess you can purchase them outside of working for Google or Alphabet. That was never obvious to
Apparently,
me.
that you can do it. But the other way to answer that is like a lot of that technology is in sort of FPGAs and these heterogeneous devices that other companies are creating, which you can buy.
Yeah, that's fair. Okay, good way to think about it. Yeah, thanks. All right, well, I'll hold on my other question because it sounds like Jack has one. Jack, go ahead.
Sorry. Okay. Hey, thanks, Hyder. I was wondering if we knew, I mean, I don't know how tested it is, but how the memory usage, I guess, kind of decreases if it decreases at scale, or I guess how that, could you maybe like speak to that a little bit?
Do you mean the computational usage or the memory usage?
Well, I suppose a computational because it changes from like a CPU intensive process to like a PGA or GPU. So I guess I don't know how
Yeah.
that.
So, like the picture that I show in the bottom is the most ideal case in all of this, right? And the exact answer to your question actually depends on what the algorithm is and how well you can write it, right? So there's some algorithms, like for example, let's take matrix multiplication for 2 seconds, right? In matrix multiplication, that's a perfectly parallelizable system, right? So you can perform all of them in parallel and then sum them up if you need to. So that one will scale perfectly. But if you have some algorithms where there's some complex interdependency, it actually depends on how complex that is and what that interdependency is to understand what the scaling behavior of that might be. So in those cases, it doesn't scale perfectly. And if you don't write it properly, then it won't scale it at all. I don't know if that sort of
Yeah,
answers
no.
that question.
So does it show? Is it simply like I guess like a compute theoretic kind of limitation, or is it like hardware dependent? Like FPGAs, are they
Yeah.
better suited for specific tasks than like I guess it would have to be how you
Like I think
kind of
the
set it
answer
up.
to your question is yes to both of them. And I've been saying that a lot lately.
Okay.
Like for example, take GPUs, right? GPUs are something that we have in every single computer at this point. They work efficiently, quite efficiently, if you know what the size of your problem is. Like if you know, for example, you feed it 10 hits and you're going to get 10 tracks out, very good. But if there's variability in the inputs and the outputs, then it doesn't scale that well. So that's an inherent sort of hardware architectural level limitation. While on the other hand, these like TPUs or FPGAs, they really depend on how you code them, how someone will write them. And that, depending on what assumptions you make, can have different scaling behaviors.
Okay. I think that answers it. Thank you.
I can ask my other question, but I'd rather let the students ask questions. No? All right.
Okay.
So, Hunter, you know that the minute that anyone proposes things like, using GPUs or FPGAs, the instant question you get from the old guard is, how robust those methods are. And so, I know we have some answers, but I'm curious to hear your take on how robust these methods will be to dead modules or sensors or alignment or other issues that are unforeseen, and how quickly one can, update algorithms, to recover losses compared to more traditional approaches.
I think that question, I don't like that question, to be honest, in all of this
All right.
because no. It's because like take the common filter, right? Example that I showed. That one works really well if you know the alignment of if you know exactly where the detectors are, what the alignment is, right? And if you
Yeah.
take the common filter at its like core, then it has the same exact issues as all the other algorithms. Then someone spent the time to put some knobs into the system to do the alignment.
Right.
And I think that's where the question, I think for me, like the question that you asked answers itself, is that we're designing the algorithms. We have to figure out what are the appropriate knobs that we put in to make sure those things are tunable
Well,
ultimately.
but I can rephrase the question, which is, if the alignment shifts, you have to update alignment tables or update some training or that sort of thing. And
Yeah.
do we foresee, machine learning approaches being less sensitive or more sensitive to things like alignment? Forgetting the knobs that you have to tune to, you have to write an algorithm that, takes the express stream and automatically trains a neural network, or takes the express stream and automatically generates a new alignment table. You can do both of those, but which algorithm is more sensitive to changes in alignment, let's say? do you think?
Like I think okay, obviously I think the machine learning parts are more sensitive, right? Because we don't have direct access to the matrices or the numbers that we're encoding in, right? They're in some weird representation that we probably cannot understand very easily, right? But at the same time, like for example, if the alignment's an issue for machine learning and we're training it on global position, we can change the local to global transformation for every event, and that will redo the alignment.
Sure. Yeah, there are ways around it. Sure.
So I think the answer is also the same. The common filter by itself is very sensitive to alignment. I think maybe slightly less, but not significantly less than any machine learning algorithm. And we've put in the knobs to correct for it. And I think that's what we have to do with this ML algorithm for anything that we do. We have to figure out which are the appropriate ones as we develop these algorithms to put them in to the entire system.
Yeah, I guess there's a challenge like, well, we've discussed, the extrapolation algorithm, but even things like, graph neural networks, has anybody studied what one does when you have missing, dead modules? Like, I think that's a big question, is it possible to design the algorithms to still work?
I feel like I'm going to give you the same answer that I gave at the Atlas week. It's under study. We don't know the answer to the question that you're asking.
Fair enough. Yeah. I mean, I think you're right that it's the Kalman filter. We know how to do tracking. We have the experience in writing the software, and so it's already been studied. Is I guess the way to think about it.
Yeah, like there's 50 plus years of research versus like 5, 10.
Yeah, yeah.
So I think we have to do the catch up on a lot of these new ideas, and that's where I think it's slightly different to think about. Is like how do we take some of the information that they have solved and solve it and implement it for ourselves.
I guess one can ask the related question, which is, things like graph neural networks and, convolutional neural networks for image processing have been used outside of particle physics for a while to look at images, let's say, like, from a camera or something. And so people have studied this, presumably one can be sensitive to camera misalignments or dead pixels in a camera. And so I guess, do you know if anyone in, who works on self-driving cars or who works for Google and academia knows these sorts of things? Maybe have we actually thought about that? I don't know that we have.
I don't. It's something. It's a question that I think about that I haven't acted upon because I do think the whole self-driving car and the error correction that needs to go inside there and the robust decision making, they must have solved some of these problems.
Yeah. I mean, you have something. Yeah. You can easily have pixels in your camera that don't work quite as well, or there's a tiny speck of dust on there, and you don't want your car to stop at that point. So yeah.
So maybe that's something that we should look into and see what we can do.
Yeah, I don't know where to direct that conversation, but about that. That's for you. Yeah. Anyway, for offline. All right. Since I occupied a lot of the conversation, I'll go back again to other people who want to ask questions. No one has any questions at all? Come on. Any have final thoughts from people?
Happy to answer any question.
I can ask a only slightly related question because you have this slide up. Do you know anyone who has a great example of Kalman filter for tracking that doesn't involve a huge infrastructure that one can actually follow? Because there's a good examples of Kalman filters for, image and pattern recognition and stuff like that. To see a simple example of a Kalman filter for tracking that works in something standalone, I've yet to find.
I have not found one. I was talking about this yesterday with another friend because she was trying to do something very similar for financial modeling, right? Because they have to do very similar things where they observe a new data and have to update their state vector. And she couldn't find anything either from any sense that is very easy to understand because it becomes very complicated very quickly.
Yeah, I mean, there's lots of examples of like, here's an image, and then you have something moving across your image, and you can track the trajectory, and that is more doable. But once you start involving tracking detectors, it's a slightly different question. So the formulation is slightly different, and I've yet
Yeah.
to find a good example. And I've been wary of trying to implement it myself. Maybe I need to. Um,
I'm hoping my friend does it for the financial modeling stuff and we can steal it from her.
That's fair, but even then, it's still not the same question, right? You need, I mean, you need like, there's open detector data and stuff for TrackML data, but you need like the correct data set too, you know, as well. So
But are you talking about the core algorithm or the actual tracking infrastructure to read and do
both.
tracking?
I mean, I think it
Okay.
would be awesome to have an example of a set of hits with positions, and you have a seed, or you'd have to design an algorithm that has a seed, and you
Yeah.
actually follow the trajectory of your charged particle. You can track it in the detector, you know.
No, I have not seen that level being very simple. It's just convoluted code at the end for
It, it
me.
it would be rather fun to have, but yeah, okay, not for you or either. Right? Okay, let me ask one last time if there's other questions from anyone. So if not,
I have a question.
great, go ahead, Frank.
So for the tracking, where is the training data coming from? Like, where's the truth table for the input?
So usually we have simulation. So we simulate. So all these pictures that I show, right? We simulate the physics process, and then we have these ginormous physics extrapolation tools like Xion, which propagate a charged particle in a material, and we design the geometry and we sort of write it in that framework, and then we reconvert it back into simulated signals and then run the entire reconstruction chain on them. So it's something that we generate and then feed into the training. Does that make sense?
Yeah.
Okay.
There's computational complexity in generating the training data too. Yes.
Yep.
Separate question. A good question, Frank.
Hello. Hi, me and Hayden have a question.
Oh yeah, go ahead, Fatima and Hayden.
So since the data is coming from simulated data, that means this process heavily relies on theory. Is there space for there to be like unexpected flags, or I guess to find like new physics that isn't expected?
Wait, so is the question more related to tracking or general like searches for new physics and looking at sort of differences with what we expect?
A little bit of both, because I think the kind of way we were thinking about it was if you're using simulation data to kind of train the machine, then if you're having output in the machine, if this was like, say this was implemented and we were using this in a detector, and you start getting some kind of decays or some kind of output that wasn't necessarily expected, or maybe was on the fringes of the simulation data, would this be something that would just be flagged, or are we assuming that we would the simulation would be up to par to the point where we would be expecting any possible outcome for the network to look at?
So I think there's a couple different questions in there, so I'll try to answer each one of them. Let me know if I don't. So for the first part of it, like when we actually like try to solve the tracking problem, right? We try to choose processes that are as independent from a physics process in the background as possible, right? So we actually may not even simulate an actual proton-proton collision. We might just randomly sample, let's say, a single charged muon and how it propagates through the detector and change different like properties of it and try to cover the entire spectrum there. So in that sense, we try to choose a training data set that is independent from the physics, so the tracking does not get biased by our simulation. Secondly, at this point, we have also had many, like almost a decade of running the Atlas detector at the LHC. So we have gone in and tuned our simulation to match data in different control regions and different phase spaces to the best of our ability. And we've tried covering all the tiny little details that may exist that can bias this thing. And then ultimately, I think even after those ones, there are concerns about new physics biasing what we do. And in that sort of area, we try to guess the best weird new physics that might exist, and then run it in simulation, and then see if our algorithms are biased or not. So we can maybe simulate some dark matter candidate going through, see what signature it leaves, run our algorithms, and see if it's biased or not. If it's biased, we try to account for it as best as we can, and then try to run the system. Can we catch everything? Probably not. But we try to cover as many classes of signatures that may exist that we can simulate and think about. And then even on top of that, there are actual analyses and searches that look for, despite doing after all of them, are there still any weird signatures that we have not captured in our simulations, and try to see if we can find new physics that way. I think those were the 4 questions that I heard.
Yeah, that seems like it made a lot of sense for what we were asking.
Thank you.
Okay.
Thank you.
Awesome. I see Alex, you got a hand up.
Yeah. I was just wondering if you have any recommendations on someone that would like to learn more about machine learning, any sort of websites or books or, papers or anything.
So honestly, in my opinion, the best thing is that there are these Keras tutorial or TensorFlow tutorials that Google themselves have provided. So if you want to run just very simple bare metal machine learning, those tutorials are very good and very accessible to basically everyone if you want to go through that. And then there are classes online that exist which teach you, let's say, the math and the theory behind it. There's tons of that are available for free. So I think MIT has open coursework there. That is if you want to go that route. And I think if you want to do the physics and ML route part of it, and let's assume you have a tiny bit of background, there are these Kaggle open data challenges that you can take part in just to sort of see what you can do. Or I think the best way to actually do that connection is to try seeing if you can find a professor that you can potentially work with, maybe Jared, so we can answer some of the questions that we were talking about. Shameless plug there.
All right. Thank you very much.
But if you want these things and can't find them, just maybe Jared can give you my email and then I can try sending them to you.
Yeah, I'm happy if anyone wants to bother, happy to pass his email. So all good questions. Any others? All right, well, I don't see any hands or hear anything. So Haider, thanks again for answering questions, for giving people a lot to think about. That was great and very much appreciated. I hope you will go eat some dinner or grab a drink and go pass out asleep.
So it's dinner time now.
Very good. Bon appetit. And thanks a lot for everyone for joining. We'll have a good afternoon, everyone else around here. All right. Bye-bye.
Bye, everyone.